Another thing, if you didn't know it already, some of you may have just come from a trailer, but they took out our thermostats that we had control over, and they put in a digital thermostat, which we don't. So, like when I got here this morning, it was way too warm in here, and I can't dial that down. And so most of the teachers, what are they going to do? They're just going to open up their doors, which is going to make the thing, if it's like doing it because it's cool outside, it's going to make it pump out even more heat. So they're not going to save any energy by doing that. It's going to actually probably cost them energy. They should just give us our controls. But at this point, we don't know that they're going to do that. Okay. Okay, so today we talk about, it's a new concept for us called vectors. And everything that we do pretty much from now on uses trigonometry. We're really done with the trigonometry portion, but we learn trigonometry because we're going to be using these functions from now on. But a vector is some kind of a physical quantity that can't be just represented with one number. Generally, you talk about a magnitude or the size of something and a direction. Magnitude, direction. So sometimes we get confused about even that word, magnitude. Magnitude means size, right? Or when you're just in a two-dimensional world, it's absolute value, right? The absolute value of something. And then it has a direction. So for example, wind is a great one to use as an example of a vector, because the wind has a wind speed, and it also has a direction that it's coming from. Right? So we need to have a way to represent that kind of a quantity. It's got a magnitude and it has a direction. Force could also be something. I mean, if you take physics, if anybody's taken physics, then you've dealt with force, and you've probably dealt with it as a vector already. Right? A force can be applied, right, in any particular direction. I can push something or I can pull it. That changes the direction on it. And velocity is a word that we actually use. In your mind, if it said, what does velocity mean? You would probably say speed, right? But actually, velocity is a vector which has a magnitude, and the magnitude is called speed, right? And it has a direction. So I can have a velocity that's taking me, in this direction or that direction or that direction. However fast I'm going, that is speed. Speed is a scalar. Right? We did scalars when we did matrices. Scalar just means one number. It can be represented by a number. So the speed is the scalar. The one number represents how fast are you going, and then there's going to be a direction to it also. So vectors have magnitude and direction, and these are the examples of it. So before they talk about, most of this talk about directed line segments is really just to set up what do we mean about vectors. After this first part of the first section here, we don't really talk about directed line segments so much anymore. We talk about vectors. But a directed line segment, it's a line segment that has a direction, meaning it's going to have an arrow on it, right? So you can see it starts at P and it goes to Q, and there's an arrow on this end. You can see that. That's what makes it directed. And it has an initial point, and it has a terminal point. So when you draw a directed line segment, the magnitude is the length of the segment. Right? The magnitude is usually represented by how long is the arrow. And the direction, you can see the direction, right? You can see this one going off towards, however you want to say it, quadrant 1, towards the northeast, whatever your frame of reference is. So magnitude and direction. Now, if you look at all of these here, they're all the same length arrows, and they're all in the same direction, meaning they're parallel. Right? When the directed line segments have the same magnitude and direction, they're called equivalent. Equivalent. And if you take the set of all the directed line segments that have that direction and that magnitude, then that is a vector. It's a vector that has exactly that direction and that magnitude. It doesn't necessarily have a position, right? Because you could move it around, whether it's here or here or here. It's still the same magnitude and direction. But that's what we mean by a vector. A vector is the magnitude and direction of a directed line segment, or, it could be a whole set of equivalent directed line segments. So usually the way that you're going to, when we write about vectors, then we can say them in two different ways, right? You can use the PQ and then put an arrow on the top like that. It's usually like an arrow which only has one side on the front of it there, right? That's a vector. Or you might use a lowercase letter and do the same thing. In your book, that's not what it looks like. In the book, they use bold. If they want to use a lowercase letter v to represent a vector, it's in bold. That means it's not a scalar. It doesn't represent just one number. It's a vector. So we have a hard time to draw a bold v versus a not bold v when we're taking notes. So we generally are going to do it by putting a little arrow on the top. That means this is a vector. Right, the book. Now you'll see some of that because I've copied a lot of their examples. That you'll see they're using bold letters. We can't. So showing that two vectors are equivalent. In a way, I think they're kind of sloppy on the way they're using this, because actually what those are two directed line segments, right? So again, if we're going to do this, then we have to determine if they're equivalent, they have the same magnitude and the same direction. So we're going to have to compare those two things for this. I think I've got, yeah. On this first one, let's compare the magnitude. Let's compare the length of those arrows. Okay, how do I determine the length of a segment in the coordinate plane? What formula do we use? Distance formula. Okay, so for the magnitude, right, the distance formula is this: the square root of x2 minus x1 squared plus y2 minus y1 squared. And we've got the x1 and x1, y1, x2, y2 for both of them. So you just do it twice and see if you get the same thing, right? For the PQ, let's do PQ first. Right, it's going to be 3 minus 0 squared plus 2 minus 0 squared, which is the square root of 9 plus 4, the square root of 13. And then we'll do the RS here, right? That will be the square root of, 4 minus 1 plus 4 minus 2. Which is the square root of 3 squared plus 2 squared, which is the square root of 13. So they have the same magnitude. Now, what can we measure to determine whether they have the same direction? Slope, right? So now we'll do the same thing with the slope to see whether they have the same direction. So now let's do the slope, right? So for the direction, right, m equals y2 minus y1 over x2 minus x1. So I'm going to do it like this. I'll say m, and then in parentheses, I'm going to say PQ and that will be 2 minus 0 over 3 minus 0. And for the slope of RS, 4 minus 2 over 4 minus 1. Right, if I simplify, that's 2/3, that's 2/3. So they have the same slope. So since they have the same magnitude and the same direction, they're equivalent. Okay. Come on, don't mess up on me again. So the component form of a vector, notice that these are angle brackets there, right? They're not curved parentheses, right? Those are sharp angled brackets. And you could think of it as this was the x2 minus x1 and y2 minus y1, like that. Or if you've already done the subtraction, then if the vector is v, notice that's the bold v, then v1 is whatever the result of that subtraction is. For us in the last one, that would have been 3, 2, right? So going to the last one, that would have been let's say for the PQ, it was 2/3, okay. 3 minus 0, 2 minus 0. And that meant it was 3, 2. Sorry. I got a feeling we're going to have trouble here today. So that's what we mean by a component form of a vector. And the magnitude of it, again, it's a distance formula, which, if you've already done the subtraction, it looks like that. If you haven't done the subtraction, then it looks exactly like the distance formula. Okay, we'll get to the direction later, but in terms of the component form from which we can tell what the magnitude is, that's it. Distance formula. Okay, now in order to say the magnitude, it's like double absolute value brackets. See that? It's the magnitude, that is a bold V inside, which means it's a vector. So the magnitude of V is double absolute value looking kind of thing. Right, that's what those symbols mean. If the magnitude of a vector equals 1, it's called a unit vector. Right, just like when we did the unit circle, what did it mean for a unit circle? It meant the radius was 1. So when the magnitude of a vector is 1, it's a unit vector. If the magnitude of a vector is 0, that is called zero vector. And if you can't see it there, that is a bold 0. So, we would write it like this, 0 with an arrow on the top. And it would mean necessarily that the component form is 0, 0. If the magnitude is 0, it's got to be both components are 0. Now again, if you look at the title of this lesson, it's vectors in the plane, right? Vectors on a flat surface. So we only have 2 components. After we do these first couple sections, or it's actually 6.3 and 6.4, then we go to chapter 11 where we deal with vectors in space, which means there's going to be 3 components, right? There'll be this direction, and then an up and a down. But for right now, that's the vectors because it's in the plane. So finding the component form of a vector, given an initial point and a terminal point, right? Find the component form of the vector. So, and we're using V, right? That's a bold V, so I'm going to use a V with an arrow on the top like that, right? Which is V1, V2, angled brackets, and now I'm going to subtract. It'll be, for the V1, it'll be, let's see, the terminal point is -1 minus 4, comma, 5 minus -7. Right? Going from the terminal point minus the initial point. Right. And so then you can simplify. So that'll be -5, +12. Okay, now that's the component form. It also said find the magnitude. So again, the magnitude, I'm going to write it like this. The double brackets, the magnitude equals the square root of V1 squared plus V2 squared, which is -5 squared plus 12 squared. Which is 13. That's Pythagorean triple, 5, 12, 13. Again, when you're doing the checkpoints, you're going to have their work and their example above it, right? Which is exactly this. Good. Good. Okay, the sometimes called simple vector operations would be addition, subtraction, and scalar multiplication. And again, we dealt with scalars before when we did matrices. That was when you just multiply on the outside of the matrix by one number. And how did that work? You just multiply everything inside by that number. Okay, that's what scalar multiplication is. Addition and subtraction, right? If you've got two vectors, here's the component form of two vectors. Here's U is U1, U2, and V is V1, V2. If you add them up, you add up the components, right? U1 plus V1, U2 plus V2. And if you multiply a vector by a scalar, right? So notice the difference that K is not bold, but the U is. But that's scalar multiplication. And when you do that, you end up multiplying both components by whatever that scalar is. So KU equals K times U1, U2, which is KU1 comma KU2. It's probably how you would just guess it worked. That's how it works. Good. Slow me down. Now, graphically, what it means, if you add two vectors, like here's the U vector and here's the V vector. If you say U plus V, graphically what it means is you're going to take one of those vectors and put it on the end of the other. Right? So this is telling you go a magnitude in a direction, and then you take the other one and go that magnitude and direction. And if you connect that initial point with that terminal point, that's the addition. Right? That's those two vectors here. Here's the U and here's the V. So the U plus V is the vector that goes from the initial point for U to the terminal point for V. Or if you would have like added the V, right? Here's the V, and then add the U on to the end of it, you're still going to get to the same place. Okay, so it doesn't matter the order you add them up. But graphically, that's what it means to add vectors. And you're going to have to add vectors by the end of this lesson. You've got to add them in real world kind of situations. So when it says add them up, that just means add up the components. And you got a new vector. that the right direction? Now, I didn't say anything about the subtraction, but in order to talk about the subtraction, understand that if you multiply a vector by -1, scalar multiplication, then you get negative the vector. So if v was v1, v2, then negative v is negative v1, negative v2, right? It puts a negative on both of them inside. And then we can think of vector subtraction is u minus v is like u plus negative v. It's really the same way we do with subtraction of scalars, right? We define subtraction for real numbers as plus and negative. I mean, it's the same thing. The book doesn't use subtraction as an example. They just say the simple vector operations are vector addition, scalar multiplication. But then subtraction ends up being part of it. Now, graphically, scalar multiplication is like this. If you had a vector v and it was this long, right? If you multiplied it by a scalar of 1/2, that would make it 1/2 of the size, right? It would make the magnitude 1/2. Did it change the direction? No, it's still got the same direction, but it does make it half of what it was. If I multiplied it times 2, then it makes the magnitude times 2. Right? If I multiplied it by a negative, and I make it the negative of the vector, instead of going from here to here, it goes the opposite direction. And again, they showed one more, -3/2. Okay, the negative is going to flip it. The 3/2 is going to make it go from this to this. Right? It's like 1.5 times this is this. So that's what it means graphically, scalar multiplication. Okay, so vector operations. If v is defined as -2,5 and w is 3,4, then find each of the following. Now, the thing you got to keep in mind, because we're going to make these mistakes all the time, is that when you're looking at these here, you notice the angle brackets. That means these are vectors. They're not initial points and terminal points. Right? If they're initial points and terminal points, they're in round parentheses, and they're going to use those words. So don't look at a problem like that and try to do, terminal minus initial, because that's not what you've got. So let's see, 2v, right? 2v. 2v equals 2 times -2,5, which is -410. Right. W minus v equals 3,4 minus -2,5. So just subtract, right? 3 minus -2. 4 minus 5. Which is 5, -1. And let's see the last one, v plus 2w. V, -2,5 plus 2 times w, 3/4. Right, that'll be -2,5 plus 6/8 Now, just vector addition, -2 plus 6, 4. 5 plus 8, 13. Now, if you remember anything at all about matrices when we did that, I mean, vectors are matrices. They're just matrices that have, it's a 1 by 2, right? It's 1 row, 2 column matrix. That's what a vector is. So these operations, we did these with matrices already, and they work pretty much the same way. Now, these are the properties of vector addition, scalar multiplication. Most of them should look familiar with things that you've done in the past, like if you change the order of the addition, it doesn't matter. What do we call that property? Commutative, right? And if you add the 0 vector to any vector, you'll get the same vector. What was that? Identity, right? So it'd be like an identity vector for vector addition. C times du, where u is the only vector in there, is the same thing as CD times u. So we moved the parentheses. Do you remember what that was called? Associative, right? So we don't care about the names for these things, but these are properties that we've dealt with in different ways. That looks like a distributive, this one, right? When you take the absolute value of a scalar, right, you don't need to have that inside the magnitude thing. You could pull that out, just call that absolute value, right? And then you still got the magnitude of the vector. There's another kind of associative looking thing. This is an inverse. This is a distributive, just on, now it's distributing a vector onto 2 scalars that are being added. And then 1 times any vector is the same vector. 0 times any vector is 0. Right? Same properties that we use with real numbers. No surprises. Okay, now any vector that's divided by its own magnitude is a unit vector in the same direction. And we're asked often to find a unit vector in the same direction as a given vector. So if I take v, right, is a vector, and I divide it by the magnitude of v, then I get a unit vector, and it's in the same direction. It's kind of like what we saw in the graphical, what kind of a number is the magnitude? Is it a vector? Is the magnitude of a vector or a scalar? It's a scalar, right? You're finding the size. The size is a scalar. So this is actually scalar multiplication here. So just like what we saw on the other page, the graphical representation of scalar multiplication, it doesn't change the direction. It just changes the size. And because the size of the vector is that, when you divide, it's going to be a unit vector. So find a unit vector in the same direction as this vector v, -2, 5. And then verify that it does indeed have a magnitude of 1. So again, define the unit vector, and just because they did it on the last slide, I'm going to call the unit vector u, okay? So the unit vector u will be the vector v divided by the magnitude of v. Okay, so I've got the vector v, I need to know the magnitude. So let's do that. And what's the formula for the magnitude of that vector? Square root of, okay, v1 squared plus v2 squared, right? So that's -2 squared plus 5 squared, which is the square root of 29. So here's our vector, right? It's going to be -2 over the square root of 29, 5 over the square root of 29. My writing is kind of not as crisp as it should be. Okay, now that's the first part. Find the unit vector in the same direction. That's the unit vector in the same direction. How are we sure it has the same magnitude? Find the magnitude. So the magnitude of u is the square root of, And again, we're doing this same process that we just did, like negative 2 over the square root of 29 squared plus 5 over the square root of 29 squared, right, which is the square root of 4 over the square, 4 over 29 plus 25 over 29. When I square both of those. And then when I add that up, I get the square root of 29 over 29, which is 1. Right, so remember, when you're asked to find a unit vector in the same direction, it means divide by the magnitude. And you could just think of it like a scalar multiplication. Okay, so the unit vector, we have two special unit vectors, and they are 1, 0 and 0, 1. I mean, if you looked at it, right, let me go up here, red and double, right? Right, so this is the unit vector I is 1, 0. So it goes 1 in the x direction, 0 in the y direction, right? This is called I. And the j is 0 in the x direction, 1 in the y direction. And, you know, this is a notation that you just have to get used to, because they use this to represent vectors that, what you would call a linear combination of these standard unit vectors, which looks different. But in math, the higher up you go, you find more and more they use this kind of representation, not the component form, but they're using these i's and j's. And when we get into 3 dimensions, when we get into space, it'll be I, j, and k, which will be a third standard unit vector. So let u be the vector with an initial point of 2, -5 and a terminal point of -1, 3. Write u as a linear combination of standard unit vectors. Now, what do you notice about this 2, -5? Is that a component form of a vector? No, because why? Because it's parentheses, not the angle brackets, right? So definitely this is an initial point in the plane, and that is a terminal point in the plane. Right? Now, if I was going to make the component form, I will call that u. Right? U equals -1 minus 2, 3 minus -5. Right? Which is -3, +8. Okay, that's component form. That's not what we were asked for. We were asked to make a linear combination of the standard unit vectors. Okay, that will look like this. -3i plus 8j. I mean, again, what is the vector form of I? The component form of the vector I? It's 1, 0, right? And the j, 0, 1. So, I mean, if I just substitute in for those two, this is what it looks like. -3 times 1, 0 plus 8 times 0, 1. Right? And that's scalar multiplication. That's going to be -3, 0 plus 0, 8. Right? And now when I add those up, I get negative 3, 8, which is the same thing. So this is a linear combination of the standard unit vectors. And it's another way, other than the component form, to write this, to write a vector. Good. Good. Morgan, you all right? So we can do vector operations. You don't have to convert these to component form to do the same kind of thing that we already did in a previous example, right? If it says here's u and v, do the math, 2u minus 3v in this form, right? 2u minus 3v equals 2 times negative 3i plus 8j minus 3, these are parentheses, times 2i minus j. All right, so that is negative 6 times I plus 16 times j minus 6 times I plus 3 times j. So now it's like combining like terms, right? How many i's do you have? Negative 6 minus 6, negative 12, negative 12i, and 16j minus, or actually plus 3j is 19j. What would be the component form of that? If that's a linear combination, what's the component form? Negative 12, 19. So this is the same thing as negative 12, 19. And if you look at their example in the book, they say, you know, you could have just converted these to the component forms and then do all the operations like we did the previous example. But you're not going to get away from dealing with these i's and j's. It is absolutely part of dealing with vectors. You've got to deal with the standard unit vectors. You good, Morgan? Okay. Now the angle, right? Everything there we've dealt with magnitude, so we didn't deal with the direction, right? If you have a vector v, it has a component form of v1, v2. Remember that v1 is all in the x direction, and the v2 is all in the y direction. The angle, the direction angle, is the positive angle with the positive x direction, right? So that's the angle right there. That's the theta. Theta is the positive. That means counterclockwise, right? When we studied angles, that's the way a positive angle goes, with the positive x direction. Not necessarily saying the x-axis, because it's not necessarily on an axis, but. And if I wanted to find that angle, well, what relationship is it? That's opposite and adjacent. That's tangent. So if I want to know what the theta is, the tangent of theta is v2 over v1. That's that. Right? So if you want to know what the theta is, take the tan inverse, v2 over v1. Now, that leads to one more way to represent a vector. And the way to do that is, notice that here's the magnitude of the vector, which is outside of the angle brackets. And then inside is cosine theta, sine theta. Right? Now, what is the if I didn't have a magnitude vector on the outside, then the cosine theta sine theta, what is the magnitude of that? What is the square root of cosine squared plus sine squared? It's 1, right? Which is, so that what it means is that this has a magnitude of 1. The entire magnitude of the vector is represented by this, which is outside the angle brackets. So you could write it like this, or you could write it like this. Now they're using the round parentheses, and it's cosine theta I plus sine theta j. And that is, that you'll see in the problems that we do coming up, that that is the way we get at the components. In the real world, when it's telling you, the plane's flying that fast and that direction, you're probably going to end up representing it like that. So let's find the direction angle for a couple vectors. Now, this u vector, both of them are written with linear combinations of the standard unit vectors. But you can tell by looking at them what is the value of v1 and what is the value of v2, right? What is, for this one here, what is the value of, well, that's not a good one. Let's do this one. V. What is the value of v1? 3. What is the value of v2? -4, right? So if I write this in the component form, v1, v2, right, then it is 3, -4. So if I want to find the measure of the angle, I'm going to do theta equals tan inverse of -4 over 3. And instead of number crunching that, I'm just going to read their answer. Finding the direction angle B, it's about 53.13 degrees. And I think you can just assume that everything we're doing now is in degrees, not radians, degrees. This one, it's a little harder in terms of the V1 and the V2 are the same thing, right? So in the end, it'll be theta equals tan inverse of 3 over 3. Theta equals tan inverse of 1. I think I got a mistake on that. Sorry. Yeah. Let me finish this one up. What is the tan inverse of 1 in degrees? 45 degrees, right? That's root 2 over 2, root 2 over 2. There you go. So this one is theta equals 45 degrees. This one, I just read off the book and I didn't read it correctly because in the end, let me do this. Erase, erase. I mean, let's just take the tan inverse. Remember, when you're doing inverses for tangents, you're only going to get answers in between -pi/2 and pi/2, or -90 and +90. That's a -4/3. Which quadrant are we going to be in? We're going to have to be in the 4th quadrant, right? So that's why my angle couldn't have been right. So let's do this. Mode is degrees. So second tan inverse -4 divided by 3. And that is -53.13 degrees. Okay. Now remember, our direction angles are positive angles with the positive x-axis. This angle here is down here somewhere, right? That's -53.13 degrees. we need that angle. So how will we find that? Add 360, right? So if I add 360 plus 360, 306.9, 87 degrees. Okay. So direction angles, tan inverse. Just, I mean, that's the 1 point so far. There's the trigonometry. Right? That's why this stuff comes after the trigonometry stuff. So now we've got 3 word problems. Find the component form of a vector that represents the velocity of an airplane descending at a speed of 150 miles an hour at an angle of 20 degrees below the horizontal, right? There's the picture. So it says find the component form. So right now, the form that we're going to have to use is like this. We're going to have to use the V equals the magnitude of V times the cosine of theta sine of theta. Now, the magnitude of the vector is the length of the vector, and you already know that. Right? Remember, our formula for calculating the magnitude of a vector is when you have the components, then you use the distance formula and find the magnitude. But we know that this plane is going at 150. That's the magnitude. There's no work to do there at all. Right? The magnitude is 150. Now, we just have to fill in for the direction angle of theta. And what is the direction angle? If it's going the way they've drawn it here, right, the positive x-axis is here, so it's 180 to there, but it's 20 degrees below that, so it's 200. Right? So theta equals 200 degrees. So cosine 200, sine 200. And again, that's a scalar multiplication, right? You're just going to multiply 150 times the cosine of 200, 150 times the sine of 200. 150 cosine 200. Negative 140.96. And 150 times sine. Where's my sine? Of 200. Negative 51.30. So that's the component form. So where did it start? It started with that one. Easy? Okay. This kind of question gets asked over and over again in this section and in the next section too, where you've got something on a ramp and there's the weight that's pulling it straight down, and they're going to ask you something about what force is necessary to keep it from rolling backwards, or they're going to tell you the force and ask you the weight, something like that. So we're going to see this a lot. So before we do the problem, I just want to set up the geometry a little bit on the next slide. Right? When you're looking at this kind of a picture, what you should be noticing here is that the weight of they're saying the boat and the trailer is this line right here. It's a weight. Weight is a force vector, right? Weight, just like velocity has a magnitude, which we call speed, weight has a magnitude which we call mass, right? But the weight, when somebody says something about weight, that is not just the mass of the thing, but it's also the direction. It's going straight down with gravity. So this vector right here, that is the weight of whatever's on the ramp. Sometimes it's a boat, sometimes it's a truck, sometimes it's a motorcycle. You know, these problems come up all the time. So this is a force vector, and it's going straight down, right, with gravity, because that's the way gravity works, right? Now, these two, right, if you draw this right triangle there, these components are, one of them is going perpendicular to the ramp, and the other one is going parallel to the ramp. If I add these two together using vector addition, I get the resultant, which is called the weight, basically. Okay, now, when it comes to, they're always going to tell you what the incline of the ramp is, meaning what's this angle right there. But because of the geometry of the thing, this angle has to be the same as this angle right here. So in this right triangle, whatever is the inclination of the ramp, that's that angle too. Because just think of it, these are all right angles, right? That's a right angle, that's a right angle, that's a right angle. We know that if that's a right angle, then this angle plus this angle add up to 90, right? But this angle plus this angle add up to 90. So these two have to be the same thing, because both of them, when you add it up to this angle, add up to 90. That's why this angle has to be the same as that angle, right? And this is parallel to this. Okay, so in every case, we're going to end up drawing a triangle, something like that, so that we can calculate. Usually it's either we're going to know this so we can calculate that, or we're going to know that so we can calculate this. So now we go back to this problem again. A force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees from the horizontal. So there's the 15 degrees. And they're saying that the force is this direction right there, 600 pounds. Which I have a little bit of a problem with, because if that's what's pulling it up the ramp, then it's actually moving, right? It's not just balancing the weight which is pulling down, because if that was the case, it would be still. It actually says it's moving. Most of these problems, they make clear that it's not moving, so that those two forces should balance. And here we're just going to say that it does anyways. Okay, so let's see. What we know is in our triangle here, just like I showed in the last slide, if this is a force that's pulling that direction to keep the thing from rolling backwards, let's say, then this parallel force right here, which is caused by the weight going down, must exactly balance whatever that is, right? If that's a positive 600, or that's a 600 going in that direction, that side has to be 600 going in the opposite direction. They're balanced. That's why the thing is not moving. So if I draw this triangle, here's my right triangle. This is 600. That's a right angle. Find the combined weight of the boat and trailer, meaning find that side. Right? Now, we know that this angle here is the same as the 15 degrees. So if that's 15 degrees. So which trig function can I use to solve for that side? Right? With respect to this angle, this is opposite and hypotenuse. Which function is it? Sine. So you're going to say the sine of 15 degrees equals 600 over x. So x equals 600 divided by the sine of 15. So just put that in the calculator. $2,318.22 pounds. I mean, in the end, it's a fairly easy math problem. I mean, it's a basic right triangle trigonometry, as long as you can get it set up correctly. Okay, in the next section, when we start dealing with not just basic vector operations, it turns into a much, probably conceptually harder problem to visualize what's going on. But in the end, the math ends up being the same thing anyways. But. Okay, then the last problem, right, and there's another typical kind of thing, and it's another one where we're using bearing as a concept. And if you notice, there were times when they used bearing in one respect, in one way, you know, how many degrees east or west of a straight north-south line. And then there was another kind of, in some problems, where they dealt with bearing as, you know, the number of degrees going clockwise around from straight north. And they use both in this problem, which is, I wish they wouldn't do it, but it's there. So we need to know how to deal with it. So understand, the airplane is traveling at 500 miles per hour and has a bearing of 330 degrees. So they've shown it in this picture here. If it's 330 around to here, then what is this angle here? Right? If it's 330 that goes all the way to there, then this has to be 30 degrees. And that's why this positive angle with the positive x-axis is 90 plus 30, 120 degrees. Right? That's where they got that from. Now, when the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour, there's magnitude, okay, in the direction of north, 45 degrees east. So now they've switched to the other way of doing bearing in the same problem. So here's the V1 vector represents the plane. Now it runs into a wind, which is hitting it from the side, you know, at this angle. And the resultant vector will be, this is where the plane is actually flying. Right, this is what the indicated speed is. This is what the wind is doing. In the end, it's going here to here. So the question is, what is the resultant speed and direction of the plane? Yeah, how do we find this vector right here? Well, we're going to have to add V1 plus V2. How do you add vectors? You add the components. So you're just going to have to find the components and add them up. Right, so let's see. So the V vector, the resultant vector, is the sum of the V1 plus the V2. Right, the V1 vector, again, using this magnitude of the vector, 500, times the cosine of 120 and the sine of 120. And for the wind was told it was 70 knots or miles per hour, and it was at an angle of 45 degrees, right? It was, you know, it was north 45 degrees to the east. Right? That's what north 45 degrees east looks like, which makes the direction angle 45 degrees anyways. So here's the one vector, here's the other. Now, you can turn that into the component form, just do the scalar multiplication, right? And I've already done that on the next slide. Right? If you multiply 500 times the cosine of 120, 500 times the sine of 120, you get these two numbers. And again, do the same thing with the 70 cosine 45 and the 70 sine 45, and you get these two. Now, what are we trying to do now? We're trying to add those vectors. So how do we add them? We add the components. Right? So the resultant vector equals, just add it up, negative 250 plus 49.5. Negative 200.5. And 433 plus 49.5. 482.5. So that's the component form of the resulting vector, okay? Not exactly what we were asked for. Now we need to find the magnitude of it and direction. How do you find the magnitude? right? The magnitude of V is the square root of V1 squared plus V2 squared. Second, square root 200.5 squared plus 482 squared. 522.5. And that is a magnitude that was given in miles per hour, so this is miles per hour. Which is faster than the plane was going originally, right? It was going 500 miles an hour, now it's going 522, so it's actually acting as a little bit of a tailwind to it. And then how do I find the direction angle? Theta equals, say again? Not V2 over V1. Tan inverse of V2 over V1, right? So 482.5 divided by negative 200.5. So do that. Second tan inverse, 482.5 divided by negative 200.5, which is negative 67.43. Now, does that make sense? Right? Negative 67.43. Whether or not you want to add 360 to find coterminal angle or not is going down here. Where's our plane going? It's going 180 degrees the other side. So remember, tangent has the same negative value, actually, in quadrant 4 and in quadrant 2. So that cannot be the direction of that plane. We need to add 180. So plus 180. 112.57. Okay, so that's it. So let's see, we didn't read these at the beginning. Represent vectors as directed line segments. Write component forms of vectors. Perform basic vector operations and represent vectors graphically. Write vectors as linear combinations of unit vectors, find direction angles, solve real life problems. So again, this is section 6.3. It starts on page 418. We just went through 10 examples. Everyone has got a checkpoint underneath, which is really like the one right there. So just whether you're looking at these slides or the video, or just look on top and see exactly what they did, try to repeat the same thing. There are some problems that we probably should do from the homework. We'll probably add those in our next lesson.